So far what we've done is that we looked at first order system, we looked at nth order system, we determined A1 and B1, which are the first coefficients of the S terms, the numerator and denominators. And then we also looked at a second order system, which was a way of us to segue into the nth order system. We didn't really need to do that, but it gave us additional information. We saw that you could, by looking at the time constants, you could not only determine bandwidth limitations, but you could also determine whether or not your system has complex conjugate poles. You can determine whether or not it has right half-plane poles. You could determine the quality factor, the peaking rates, and all those things. So they're quite useful information, and you can do that quite easy. So now, the next step, basically, well, the last step really, is to go to an nth order system in the most general case. And since we've built everything you needed to build so far, you should be able to do that. So again, we go to our nth system with n energy storing elements. Say C1, in general L2, etc. Let's say you have Ci, Cj, and so on and so forth. You have an input and output that are x and y. And we talked about this briefly last time, so I'm going to mention it again. The x and y are voltages and current of ports. Now, the x and y can be the voltages and current of the same port. In which case, basically what happens is that we define the input as the current of one port and the output as the voltage of the same port. What you're measuring, the transfer function, is really an impedance. So you can determine the input impedance, output impedance, or if the input is a voltage of one port and the y is the output of the same, the current of the same port, then you are measuring an admittance. So you can not only use this to determine the transfer function, but you can also determine the impedances. So, and there's no dynamics inside. Okay, so now for the nth order system, so in general, the transfer function of this thing looks like this. Let's for now assume that you have only capacitors. If you have inductors and capacitors mixed, you will have two sets of sums. Two sets of sums as opposed to one. Everywhere I have a sum, I'll have one sum for the capacitors and one sum for the inductors. But all the analysis will look exactly the same. So I'm just going to keep the equations humanly tractable. I just keep them all in capacitors. But you can imagine that everything that you have like inductors, like two sums. One sets up some with capacitors and one with inductors. So I'll just do it with capacitors for now. So if you have just capacitors, then the transfer function looks like this. So you have A naught plus the sum of what we call, these are intermediate variables. We won't use them later, but we use them in derivations, the alpha and beta. Alpha 1i, Ci, from I equals 1 to n times S, plus, so we argue that S can only appear in conjunction with a C, or an L. I mean, in that case, in the case that you have to both N's and L's and C's, you will have one sum for the C plus another sum for the L's. But it's the same kind of behavior. So you have a CS here, and you have some general coefficient alpha. So the most general form that this can have is in the following, as we've argued before. And then the second order term looks like I and J, I from 0 to n minus to J, basically, and J from I plus 1 to n. And this is another way of writing that. So this way you only get one set of them. So for instance, you get 1, 2. You don't get 2, 1. So you can keep one of the two. And basically again you have alpha 2ij, Ci, Cj times S squared. And you have higher order terms. You want there will be a triple sum here with the alpha 3ijk, Cj, Ck, Ci, Cj, Ck times S cubed, and so on and so forth. So we'll show this dot, dot, dot. And in the denominator you have exactly similar, very similar things, not exactly the same, but similar in behavior with a different set of coefficients. So this is S, I equals 1 to n, plus, and again, this is the derivation. I just want you to see it, you don't need to remember it. Plus blah, blah, blah. And these terms will be S cubed, S, and so on and so forth. Higher order terms. choice of indices. And the fact that this expression should be valid for all values of C, including 0 and infinity. So if it's valid for all values of C, then the only way this can hold for an arbitrary set of indices is that if alpha 2ij is equal to alpha 2ji. So they have to be like that. So otherwise you can switch the name of the CI as, you can call C1 C2 and you can call C2 C1, and the result will be different if you do that. If this doesn't hold. The same thing with betas. Now, in general, higher order terms, the same kind of similar thing applies. As long as you have rotational symmetry, these things should be valid. So, for instance, you can say alpha L, I, J, K, etc., S, T, U should be equal to alpha L, U, I, J, K, etc., S, T, which is equal to alpha L, T, U, J, and so on and so forth. So there should be a rotational symmetry. In other words, tau 1, 2, 3 should be equal to tau, let's say tau 5, 1, 2, 3 should be the same as tau 5, 3, 1, 2 should be equal to tau 5, 2, 3, 1. Okay? Anyway, and the same thing for betas. Anyway, so this is something to remember and know. I'm going to erase it for now. It doesn't matter. It's in your handouts. Okay, so, and the other thing is that you can't have CII squared and CJJ squared. We made that argument last time. I'm going to make it. So they cannot be equal. The reason is that you can't have, if you have something like that, if you set all the C's to 0, other than CI, let's say you have a CI squared, then you get a second order system out of a system that has one capacitor, one non-zero capacitor. So these, you can only have a cross product, you can't have a self product. Anyhow, so more or less this is what we have. And then the question is, how do we determine, so this is A2 and this is B2. We want to determine A2 and B2. So to determine B2 and A2, we do the following. So let's say we look at our system and we make some other changes. So we say, okay, let's zero value everything other than CI and CJ. And let's set CI, so we'll do the following. We'll say CI goes to infinity, CJ is non-zero, so we have CJ, CI goes to infinity, so it's shorter. And then everything else is infinite value, is zero value. So the inductor is open, the shorter, the capacitor is open. So, and in this case, if you have only capacitors, then it will be Ck equals 0 for K not equal to I. Alright, so that's for that. Now, if you do this, what happens? If you set Ci to infinity, what would be left here? So, for Ci going to infinity, this becomes what? What is left? The only term that matters in this sum would be the one with Ci. Because everything else will be finite. So you have alpha 1 I CIS here from this sum, and then you have what comes out of that? You have alpha 2 IJ CI CJ S squared divided by the same thing here with betas. And the higher order terms would be 0 too. Why? Because you still have a CJ in this, CI in this, right? You have CIs in this, which goes to infinity. But you have two things that are multiplied by that. That's at least two things that are multiplied by that are zeros. So you basically have 0 times infinity. And if they are of the same order of 0 and infinity, the 0 and infinity gives kind of like a finite quantity, 1, 0, and 1 infinity. So it's a limit, basically. You have to think about it as a limit, basically. It's just like x 1 plus times 1 over x. X going to 0. It's x squared times 1 over x, or x cubed, whatever. So those terms will go to 0. So these are the only terms that would matter. So in this, and then you can see, you have these terms that you can cancel. CIS, CIS, CIS. And what's left looks like this. You can see it's very similar to actually the derivation that we have for a second order system. And again, this is the derivation. And I won't test you on the derivation. Just like, let me tell you now, so you don't worry about it, just to see it. So this is the way it looks. Now, from a physical standpoint now, so this is the mathematics. The physical standpoint, if you do something like this, what is the order of this system? A system where everything has been, all of the other elements have been zero valued, Ci has been infinite valued, and Cj is the only non-zero element. What's the order of the system? It's a first order system, right? What is the time constant of the system? The time constant of the system is, let's call it tau j, but we should call it tau j I, because I is infinite value. We said anything in the superscript is infinite value, because since I is only, by definition, is what? Is the resistance seen by this guy, when everything else is zero or infinite value, let's call it Rji times Cj. This is the time constant. But we know for a first order system, this time constant is this coefficient. But this coefficient in the denominator, the only pole, if you have one pole, the pole is equal to the 1 over minus 1 over the time constant, right? So this has to be equal to that. So if that's the case, then basically we say beta 2ij over beta 1I Cj is equal to that. You can write it that way, Rji Cj. This is Cj. Yeah, okay. So these guys cancel. So what you're left with is that it tells you basically beta 2ij is beta 1i Rji. But what is beta 1i? They have already determined this, right? What is the sum? This is the sum of zero value time constants, right? B1. So these are Ri zeros. These are the zero value resistances, right? That's how we determine the zero value time constants. So these guys are simply R10. So this is R10, I'm sorry, Ri0, Rji. And if you plug it in here, you will see that, so therefore this guy is Ri0, Rji. And this guy is, of course, Ri0. And you can see easily that this can be written in the following form. Ri0, Ci, Rji, Cj. This is tau I0, the zero value time constant for element I. And this is this time constant, tau ji. The time constant of the jth element when ith element is infinite value. And therefore that basically says that B2 is the double sum over I and j, I smaller than j, of tau I0, tau ji, which is the result that we're trying to obtain. And so now we have to determine A2. This is A2. Now, A2 is even, actually makes it simpler. So to determine the A2, you need to go one step farther. So what you do here is that now you say, okay, I'm setting both Ci and Cj to infinity. And look at the transfer function. If I set both Ci and Cj to infinity, and I define that, so Hij is defined as H when Ci and Cj go to infinity, and everything else is 0. So I define it as that, and what do I have? So what does it, it's this thing, right? Then Cj goes to infinity. If Cj goes to infinity, what does this reduce to? was this. So alpha 2ij is simply that times hij. So A2 would be the same double sum in terms of indices, tau I0, tau ji, the same as that, same time constant, times hij. I use this. Multiply this to get alpha I2, 2ij, and plug it in. And it makes sense because alpha, A, should have the units of the transfer function. Because it's in the denominator, this whole thing, and the denominator is unitless. Because it's added to a 1. So if everything works out, this has to be unitless. And this has to have units of H. So you can only get one H. You can't have H squared or anything in here. In any of the terms, even in AN. So the same kind of, you can either apply induction, or you can actually basically look at it and do the same analysis over and over. And what you do is that then you can basically derive the A ends and B ends the same way, exactly the same derivation. You can keep going. And then you will basically see that your AN is n sums I, J, K, etc. where I smaller than J, smaller than K, smaller than all the way to smaller than equal N, greater than equal 1, tau I0, tau Ji, tau K ij, the next one would be tau Lijk, etc., times Hij, all the indices, and Bn is a similar sum, I, J, K, etc., multiple sums, tau I0, tau Ji, tau K ij, all the way, without the H. And that's it. Now it looks bizarre, or it may look a little bit complicated, but we've seen through examples that this is not actually as complicated as it looks. But to write the most general form, you have to write it this way. Okay. So that's basically the derivation of the nth order system. And now the taus, if you have a capacitor, so for instance tau, whatever, K, I, well, tau, let's say L, I, J, K, etc., if it's a capacitor, it's going to be R, L, I, J, K, etc., meaning the resistance seen by element what? L, when ports I, J, K are infinite value, and everything else is zero value, everything that's not named, times CL. And if it's an inductor, it's going to be LL divided by the same resistance. And what is Hij? Tell me, what's Hij, dot, dot, dot? What is it?
Transfer function, I, J, K, or whatever is listed is infinity.
Exactly. So when elements I, J, and K are set to infinite value, everything else is set to zero value, and it's set to transfer constant associated with that. Basically, it's a low frequency thing from input to the output. Everything is low frequency. All calculations must be low frequency. Otherwise, it's useless. Okay, so that's the derivation. Done. Now, we can learn actually quite a bit from this. So we can do several things. Let me do a couple of examples, and then we'll talk about some of the corollaries. And then we'll continue our discussion basically, and then we'll talk about the infinite value time constants. It's a special case of this. So as for examples, so let's see. So one of our favorite stages has been the common emitter or the common gate. So, and we did the zero value time constant analysis of this state with three capacitors, if you remember. When we were doing that example that when basically we tried to increase the bandwidth. You remember first we did this, and then we made a cascade, and then we put a common collector, made a follower, buffer before and after, etc. So this is the input, this is the output. And then let's assume that you have three capacitors. The same thing. C pi, C mu, and CL. And we did these three time constants. They're zero value time constants. I'm going to rewrite them quickly, but we have already done this before. So let's write the zero value time constants. Tau pi, 0. Let's do it quickly. Let's as a practice, an exercise, without drawing the small signal model. What is the resistance seen by C pi? What is the resistance from between these two nodes? Or in other words, between this node and ground? When all the sources are, independent sources are null. Right. What do you see that? Look at that. R1 and R pi. Right? Here you see R pi. So you have R1 parallel R pi times C pi. That's tau pi 0. What is tau mu 0? This is the one that was the longest. Right? You remember the R left, R right business? So it was the R left, which was this guy. R1 parallel R pi, plus R right, which is R2, plus GM effective, which in this case is GM because there's no emitter degeneration, times R left, R right. So it's GM R2 times R1 parallel R pi, the whole thing's times C mu. And what's tau L? 0. This is trivial, right? What is the resistance seen from this node to ground? R2, right? I mean, if you have an RO, it's going to be R2 parallel RO, but you can assume that R2 is already, has subsumed RO. So it's R2CL. So these we have calculated before. Now, if I want to determine the complete denominator, first of all, I know how many poles I have. I've told you the rule, right? How many poles do I have? 2, right? Because if I set this voltage to 1 volt and this to 2 volts, this is already set to 3 volts. I can't set that in arbitrarily. So, now, I need to determine B2. So what is B2? B2, if I write these indices as 1, 2, 3, I can do it in different ways, right? I mean, basically it's a double sum of tau I0, tau Ji. I and J, I smaller than J. So how many tau Ji's are there? How many different, tau mu L's and things of that sort are there? 3. Sure? There are 3.
6.
There's 6 actually. Right? Because you can have, there are 3, and then you can have either way. You can have tau L mu and you can have tau mu L. They are not equal. This is not true. That tau mu L is not equal to tau L mu. Or let me just do it numerically. Tau 1, 2 is not equal to tau 2, 1 in general. However, this is true. Tau 1, 0, tau 2, 1 is equal to tau 2, 0, tau 1, 2. Individually, they are not equal, but the products are the same. So, anyway, so there are 6 of these. But how many do I need? How many do I need? 3, right? How many terms does this sum have with 3 capacitors? Think about 1, 2, 3, right? So the terms of this sum is tau 1, 0, tau 2, 1, tau 1, 0, tau 3, 1, plus tau 2, 0, tau 3, 2, right? J has to be smaller than I, or greater than I. So, but now there are 6 of these, so I have so many choices. So I can choose which 3 I want. I can pick any 3 of the second order time constants of these, and all of them will work. But some of them are simpler than the others. Right? Some of them look less cumbersome in terms of the algebra that I have. Guess which ones they would be, based on the zero value time constants. It's a product of 2 things, right? So it's a product of one of these guys and one of those guys. It's one of these guys, these are these guys. The zero value time constants. And one of these. Which ones would be easier to calculate? The ones associated with, the ones that go with this, or the ones that would go with this?
Second one.
These guys, right? So, to get those, it means that my J has to be which one? To get as many of these as possible. Mu, right? So I have to go for after tau. I mean, this is not a rule. This is like a rule of thumb, really, right? It's a guideline. So So I'm just saying, okay, so if that's the case, so I go with tau mu pi and tau mu L. It's actually a good thing because it means that I'm looking at the resistance seen across here and one side of it is shorted. It should be easier to calculate than that. One of the R left or R right is 0, which eliminates 2 out of the 3 terms. Remember, we got R left, R right, and R left, R right product, the product. So that's good. And then the third one has to be something else. It can't, I mean, I've already done these. So I can basically pick one of the other 2. I can pick, for instance, tau pi L. Or tau L pi. Doesn't matter. Okay, so let's calculate this. What is tau mu pi? The resistance seen by this guy when this guy is shorted. What is it? R2 times C mu. Right? Makes sense? You remember? Otherwise, it's R left plus R right plus R left, R right, GM, right? But R left is 0. So it's basically just R right. So it's R2 C L. I'm sorry, C mu. This has a question. How about tau mu L? So this is the resistance seen by C mu, again, when this guy is shorted. So I just have that R left thing, right? Which is R1 parallel R pi. And how about the last one? What is the resistance seen by this guy when that guy is shorted? It's just like R1 parallel R pi C pi. So these are the 3 things that I need to do. Now I have to form the right sums, right? So, for instance, this has to go with what? This goes with which one of the time constants?
Tau pi.
Tau pi, yeah. This has to be in the denominator now. So it's this. So this B2 is, if I want to use these terms, it will be tau pi, tau mu pi, plus this one goes with tau L, right? Tau L 0, tau mu L, plus this one goes with which one?
L.
Tau L again. Tau L 0, tau pi L. Okay, so this product is this guy times that. So it's R1 parallel R pi R2 C pi C mu plus this one is tau L tau 0. So it's R2 times this guy. So I get again R1 parallel R pi R2 C pi. Okay, CL C mu. It has to be using the C's of the capacitor, the subscripts. And here, the last one is tau L times tau pi L. So again, I have the same term. R pi, R2, this is going to be C pi CL. So I can see that the resistances are the same in 3 of them, so I can factor it out. This is sometimes shown as, since it occurs in the analysis of the common emitter, this or common gate, this is sometimes shown as C triangle square. Because it said sum of the two-way products of the 3 capacitors. If C pi C mu CL C mu C pi C mu CL. And you will see this is important when we talk about compensation and pole splitting. This will have an impact on pole splitting. This product. But and if you try to derive this, then basically KVL and KCL is just like a page and a half. And we went through a lot of discussion about it. If you just want to do it, it's relatively fast. So now, but there are 3 capacitors. In general, if I don't know my rule, the rule I told you came from something, right? So I have to tell you, now I'm going to tell you where that rule came from. But then let's determine B3. What is B3? Tell me one because each one has, they can't equal and they can't go down in the way I wrote the sum. So you have n terms and n time constants, so there will be only one term, one product. So that's the only thing there is. So, and we have calculated these guys no matter which one you assume. So the question is, which one is this one? Let's assume tau pi. So let's for instance, there are many of these. There are different ones. You can pick any one you want. So you can assume you can take t tau pi mu l. That's one. Or there are like tau mu pi l. Whatever. What is tau pi mu l? Think about it. It's the resistance. Well, it's a capacitance C pi times the resistance C by C pi when what? When the other two are shorted. What is that resistance? When this guy and that guy are simultaneously shorted. 0. So that time constant is 0. Therefore, V3 is 0. This is how capacitive loop comes into play. Now you can see why the capacitive loop does what it does. Because if you have a capacitive loop, the last term will have, you are basically shorting n minus 1 capacitance in that loop. So if you have a capacitive loop somewhere, to get to this term, it means that this is one of the indices and this is the remaining n minus 1 for an n-order system. So you're shorting n minus 1 of these and saying what is the resistance seen by the nth one? It's always 0. Therefore, whenever you have a capacitive loop like this, you reduce the number of poles by 1 because you reduce the order of the denominator by 1. Because then, as this example, V3 becomes 0. That's why, the same thing with inductive loops, right? Because if you have an inductive loop and nothing else attached to it, right? Infinite valuing an inductor is like what? Open circuit, right? So if I take n minus 1 of these and infinite value them and say what is the resistance seen by this guy? What is the resistance? Infinity. So what is L over that resistance? 0. So these factors again become 0. So that's why an inductive node, not an inductive node, inductive cut set, or a capacitive loop reduced. You can easily see it. Okay, so that's one example. And that's a useful example because it talks about common emitter, which is a common stage.
Question.
Yes.
So let's say we had to solve for B3 and it wasn't 0. You can arbitrarily decide whichever 1, 2, and 3 points to however we want to map it to make it easier for ourselves.
Exactly. Actually, to be perfectly honest with you, the higher you go in this calculation, the easier it has become because there are more and more shorter things. You saw that these guys, the second order ones were simpler than the first order ones, than 0 value. And this for B3, the calculation consists of one calculation. Because you only need one. You can calculate this, for instance. Let's say it was non-zero, then you can basically take this and pick any of the two that you've already calculated to calculate that. Because these are the 0 value time constant, these are the second order time constant, these are the third order time. So it actually becomes simple. Let's actually do another example of this that has a third order. So let's quickly do that. And let's pick something with more inductors. More two of them. To keep it consistent with your handout. And please check my indices, make sure I'm consistent with your handouts. This is kind of an LC filter. So let's call this C1, L2, L3. Is that what is the indices I used? Okay. So first of all, tell me if it's a low pass, high pass. What do you think it is? It's a bandpass. Correct. Why? Right. At DC, does anything go through? capacitor blocks it, and the inductor shorts it. The two things that reduce the DC. So you can imagine right away that there are two low frequency poles. And then, how about high frequency? Very high frequency. Does anything go through? This guy blocks. This becomes open. This becomes open. So this basically just this is short. So it's a bandpass. Okay, so I know that. All right. So let's see. Okay, let's do this. Let's do the time constant. For zero value time constant, if you intend to go through the end, you have to calculate all of the zero value time constants. Anyway, you know that. So there's no ambiguity or question of which ones I calculate. If you intended to get some partial results, then you may say, okay, I'm interested in this and that, so I'm not interested in all. But if I try to derive the transfer function, which is the most general case, a lot of times you don't. Basically, a lot of times you're trying to get partial information, but you do that. Okay, so let's do the time constant, zero value time constant. So tau 10, what is tau 10? The resistance seen by capacitor when the inductors are zero value, meaning inductors are short. This is short to ground, so this is ground on this side. What do you see? And of course the source is shorted. What is the resistance seen by this guy? R1, right? Or R. So it's R C1. What is tau 20? The resistance seen by this guy when everything else is zero value. Zero value, this guy is open. This doesn't do anything. Zero value, this guy is shorted. So what do I see? R. Now, but this time this is the time constant for inductor. So it's L over R. And tau 30 is what? Seen by this guy. Again, the same thing, L over R. Done with the CVTs. Now, I have to go to the second order ones. I can pick any one I want, just basically. So if I want a tau 10, and the next one is tau 21. All of them are simple, so I don't think it matters which ones you pick. So what is tau 21? The resistance seen by this guy when element 1 is infinite short, which is what? R over 2. So what is this? It's 2L over R, right? 2L over R over 2, essentially. It's L over R over 2. Because you see R over 2. This guy sees R over 2. R and R. And then, so that gives me 1. And then I have another one, which is tau 31, if I wanted to use that. Tau 31 gives me what? Tau 31 is the resistance seen by this guy, but this is shorted. What do I see? What is the resistance seen? And this one is shorted too. So it's L over R. Okay? And I need one more. I can take this one and that one. So it's tau 3, 2. 3 and 2 is infinite value. What do I see? No, careful. This is zero value, it's open. This is infinite value, it's open. What is the resistance in here? Infinity, it's open on one side. So L over infinity is okay, so what is the second? And then I have to calculate a third order one. So I already have done these. I can take one of these two, for instance, this guy and that guy. So if I want to go through this path, I just basically see tau 3, 1, 2. That's the only thing I need from the third order. What is tau 3, 1, 2? Tau 3 and 1 and 2 are both infinite value. Well, this is infinite value, it becomes open. This is infinite value, it becomes short. So what do I see? L over 2R. L over 2R. Okay? Done. For the denominator. So if I want to calculate this, basically it becomes RC plus, so B1 is RC plus 2L over R. B2 is a three-way sum of two-way products. So if this time that R's cancel, so I have 2LC, C1. Did I use different L's?
In the handout, it's different L's.
Okay, so I can have, this is fine, it's easy, because it's an index of the subscripts. It's this index. And this is 3. So it's 2LC, this is L2. L2 2C plus whatever. The only thing that will be different here is that it's L1 plus L2. And, okay, so this is that. The second term is basically L3C plus, and the third term is 0. So it's C times L3 plus 2L2. That's B2. And B3 is this times that times that. The R's of these guys cancel. The 2's of those guys cancel. So I'm left with C1, L2, L3 over R. That's enough. Then I can write it as this times S plus this times S squared plus this times S cubed plus 1. What I want. And how about the numerator? Well, for numerators I need some other things. What do I need? The transfer constants. Okay, well let's see the transfer constants. Let's see what they are. So H0 is, we already have said that, right? 0. So how can I get a non-zero H? Let's see. If this is short, this has to be open, right? And this has to be shorted, because otherwise nothing goes through. So it means that the lowest order thing that will give me a non-zero thing would be H12, which basically this is open, this is shorted. And what is the gain? What is the transfer constant? And this is shorted. This is shorted. This is open. This is short. So this is basically resistive divided between two resistors of equal value. That's 1/2. Anything else that would do that? If all three of them are infinite value, this is infinite value, this is infinite value, then nothing gets down, and this may be shorted. So this is the only non-zero one. You can say all other H. All other transfer constants are 0. Done. So what that tells me is that my numerator looks like this. Well, you can take the 1/2 out, and basically you have S squared in the numerator, and then I have 1 plus this B1S plus B2 S squared plus B3 S cubed, which I've calculated. Oh no, wait a second. There's one thing missing actually. It's H12 times what? This one and that one. So I have to take this product. And the 1/2 cancels that 2, R cancels R, so I have L2C1. So this 1/2 goes. So that's the transfer function. You can plug these into that. And you can see it has 2 zeros at 0. And it's a third order system. So it goes like this. This is like steeper on this side than that side. So it's like plus 40 dBs per decade on that side and minus 20 dBs per decade on that side. So you got a couple of poles here, you got 2 zeros at infinity, and then another pole. You can think about them as 2 inverse poles and 1 regular pole. It's a bandpass system. And if you wanted to design it, you can even do. Because now you know what the coefficients are, you can play with them. You can actually know what affects what. So it helps you with the design of this thing. Now, there are a couple of other things that we want to talk about. So here, there are a couple more correlations. You remember the other thing that we talked about that I told you without pretty much any proof was Alex. That you remember the concept of uncoupled or decoupled poles, or decoupled time constants. You remember we said that in general, although, for instance, in the case of B1, you remember B1 is obviously the sum of the zero value time constants. And also we showed through our factorization of the denominator that B1 is also equal to minus 1 over some reciprocals of the poles. Right? But we said that in general, it's not true that the reciprocals of the full time constants are equal to that. This is not generally true. Several reasons for it. First of all, the numbers may not be equal. You know, in that example, you have 2 poles and 3 time constants. Right? In the previous example with it. Second is that the poles can be complex. Time constants are always real. So that cannot, you know, it's difficult to have a complex quantity equal to real quantity. So it's obvious they can't be equal. Their numbers are not equal. That's why I use n and n prime here. But there are certain special cases where they are. And that's when a time constant or a set of time constant is decoupled from the rest. And you remember the criteria that I gave you for this to happen? Does anyone remember? What needs to happen for a time constant for it to be uncoupled? Basically, in other words, it means that it can't be factored out of the denominator. And in that case, this will hold. This will be true. So that time constant has to be independent, has to be the same, no matter what you do to the other ports, to the other components. If you zero value them or independent value, or infinite value, it should remain the same. In other words, if you have a capacitor somewhere that's connected to your circuit, that can have other capacitors elsewhere, or inductors elsewhere, and no matter what you do to these guys, short them, open them, any combination, the resistance seen by this guy remains the same, then I claimed that this time constant is uncoupled. In other words, this guy, this really represents a pole. An obvious and trivial example is this. Let's say you have a circuit. Let's say you have a common emitter, and then on the side you have this. That has nothing to do with your common emitter. Again, this is a trivial example, but and we had non-trivial examples. A common base was a non-trivial example. 2 time constants are uncoupled. But if you have something like this, and this is sitting there by itself, no matter what you do to these other guys, the resistance seen by this guy is the same, right? So this represents an independent pole. You may say, wait a second, but this pole is not the transfer function of the system. The interesting thing is that it also represented exactly the same as 0 in the transfer function that we calculate. It's exactly sitting on that pole. So it doesn't violate anything, it works out nicely. But it will give you both a 0 and a pole in this transfer function. That are exactly on top of each other. So irrelevant. But now, where does this come from though? So let's see where it comes from, this decoupled pole thing. So let's think about, now we know what these terms look like, but let's think about the denominator. So the denominator in general looks like this. And so on and so forth, right? This is the denominator, d of s. I can write it, and I know what these terms are now, so I can write them as such. So this is sigma I equals 1 to n of tau I0 s plus this guy is a double sum I and j tau I0 tau ji s squared plus I don't know. Now let me reorder these sums. Let's say I take the nth time constant out of the sum. Tau n0. So I write this as 1 plus tau n0 s plus the sum tau I0 I from 1 to n minus 1 this time times s. So these two together are equal to that. Right? We just took the last term and wrote it separately of the sum and calculated only to n minus 1. Right? And then I do the same thing here. I take the last nth one out of here. So this becomes sigma tau I0 tau ni, okay, to go up to n minus 1 in this case. Tau I0, tau J I S squared plus higher order terms. Okay? And now I do something different. So I take this, I take these two, and I take these two, and I take this and the next one, so on and so forth. So I take that term that I've taken out with this guy. So here I have 1 plus tau n0 s. Not tau n0 s. Okay? Plus. Now, if the nth time constant is uncoupled from everyone else, it means that it doesn't matter what the superscript is. It's always the same. So it means that tau n0 is equal to tau ni for all i's is equal to tau nij for all ij's. That was the way I defined it, right? I said, well, it has to be independent of what I do to the other things. Anything in the superscript shouldn't do to anything to it. For any combination of stuff in the superscript. Right? So for any combination of those, this should remain the same. If that assumption is valid, if this is true, then this guy, all of these are the same in this sum. Independent of I. And they're all equal to this. So I can take these out and put it up front as Tn0. And if I do that, now I notice that I can factor these things out of this term, out of these two. And what will be left is 1 plus tau n0s times sigma I equals 1 to n minus 1 tau I0 s. Between these guys. And the same thing for the upper one, basically I'm just going to skip it because they become longer and longer. So it would be another 1 plus tau n0s, which would come from a tau kij, which would all be the same. Or tau nij, sorry. The next ones would be tau nij's, but since all of them are equal, according to this assumption, then that can be factored out of some double sum that goes to n minus 1. And so on and so forth. So you see, these terms are common among all of them, so I can basically factor it out of the whole thing. And this would be one order smaller. So it would be an order of n minus 1. And that can be factored out, which means that I have a pole at frequency 1 over tau n, a real pole. And in this case, this is really meaningless, so I can basically just define all of them to be equal, well, tau n, no superscript. So it would be 1 over tau n. This would be that tau n. So this is the concept of one uncoupled pole. You can see that where it comes from. So it says that if you have one time constant that doesn't change no matter what you do to the other elements, inductors and capacitors, meaning no matter what you do in terms of shorting and opening, if it's the same for all shorts and open combinations of everyone else, then there is one pole associated with that time constant. It's a real pole. It's a negative. It's a left half-plane pole if that time constant is positive. And that's it. That can be separated. And if you have a system, the rest of the system is of order n minus 1. Which is useful because then you can separate things from each other. Now, this is not, then this can be generalized actually, which I'm not going to show. Major mess. But I'm not going to prove that, I'm going to tell you what the result is. So imagine that in general you have n time constants. N energy storage element, n time constants. Now, if you have polynomial may not be factored. You may not be able to factor it in terms of real terms, that big polynomial. But what it means is that then you have basically your time constant partition your circuit into different parts. And they can be independent of each other, but mutually dependent. So these guys can affect each other, and these guys can affect each other. What is the example of this thing? For example, you have multiple stages that are cascaded and they are buffered from each other. They will have time constants within each other that will affect each other and will form polynomials within that. But the overall transfer function is the product of these three polynomials, the denominator, right? So you will have basically this condition like this. So you can actually find out that, okay, well, these three time constants are fine by themselves. I mean, they're interacting with each other, so they're coupled to each other, but they're collectively uncoupled from these guys. And then you can basically treat this part of the circuit separately and apply the method of time constants here, time and transfer constant to this one, calculate this transfer function, same here, and then the transfer function may be the product of them if they're cascaded or some other combination.
So here we're working with poles, but it's also applies
with the zeros, it applies with the zeros in the sense that as long as they're uncoupled zeros too, so basically just, but this is primarily about the poles. But if the circuits are really isolated like that, then the zeros will be isolated. Yeah.
In order to prove this, didn't you use the assumption that the number of sums in the denominator is an even number, because you have to factor out that term? I mean, you see that? You have to have not even number of terms. I mean,
no.
It overlaps.
They're overlapping, right? I'm taking the last term. See, the last one comes from that big final sum, right? So that one will always be there. If you have an odd number, right? The last one would be a single term. Yeah. Anyway, but this is a useful thing because it allows you to divide and conquer.